Well, thanks for joining us. Here we are. We're going to take a look at our homework tonight. I think we start with question 68 and go all the way through 72. One of our questions is what is it called? Checkpoint. So for linear equations, based a lot on work that you've done in the 8th grade. But let's go ahead and start with question number 68. In 68, it says use what you have learned about exponents to rewrite each of the expressions below. So if I look at A, I can see in my numerator I have 11 factors of 9, and in the denominator there are 9 factors of 9. So I can rewrite this as h to the 9th power, 9, 10, 11, times h to the 2nd. So if I look at that numerator, that's exactly 11 factors of h, right? 9, 10, 11. In my denominator, I had h to the 9th power. The reason why I chose to write it like that is now it's very easy for me to see that, well, that ink is probably way too thick for this, is that I have exactly this giant 1 in the form of h to the 9th over h to the 9th. So what that leaves me is a very clear picture that this is the same thing as h to the 2nd power. So that's our answer for A. Let's take a look at B. In B, I have 3 factors of x times 4 more factors of x. So when I do that, I know just by definition of exponents, because there are 3 factors here and 4 factors here, together we have exactly 7 factors of x. So this is x raised to the 7th power, right? And that's using the definition of exponents. Now, I know a lot of us will look at these two things and will say, oh, okay, we add. Oh, okay, we multiply. No, that's not how our thinking goes. What we have here is we have 3 factors of x times 4 additional factors of x. So that's a total of 7 factors of x. So it's not a matter of adding or multiplying, although that certainly is a shortcut here. It's a matter of understanding what we're looking at and realizing how we can represent that in a simpler form. Let's move on to A, B. Oh, there is a C over here. C, here we go. So this has 2, you can see it, there are two collections of these factors, right? Remember the base number, the bottom number tells me what I have, and this has how many copies of it. So I can rewrite this as 3k to the 5th times another set of 3k to the 5th factors. So that's what that becomes. And when I look at this, right, it's clear that I'm multiplying a 3 times another 3, and 3 times 3 is 9. I can write that there is the number 9. And then you can see I have 5 factors of k times 5 more factors of k. So that is a total of 10 factors of k. So this is 9 times k to the 10th power. Let's move on to D. Way back over here. Here's D. So I have 7 factors of n. Right? This is literally n, 7 factors of n, times an additional factor of n, right? So that means that I have a total of 8 factors of n. This is just n to the 8th power. For E, ooh, that's nice. In our numerator, we've got a 16 and the denominator is a 2. I think it would probably be nice to write this as 2 times 8. And then I'll write the over 2. So I'm just kind of taking care of just this one part first. There's the 16 and the 2. So that's taken care of. And then I have, nicely, I have x to the 4th power in both the numerator and denominator, right? So that's going to form a 1. And then finally, I have this y to the 3rd that's hanging out in the numerator. So identifying the ones, I can see I have a 1 in the form of x to the 4th over x to the 4th. And I also have a 1 in the form of 2 over 2. So what I'm left with here in the numerator is the number 8. And I am also left with 3 factors of y. So this becomes 8y to the 3rd power. And then finally for F, I'm doing some multiplication here. I know 4 times 7 is the number 28. So I can write 28. That's going to be part of my answer. That's taken care of. That's taken care of. I can see right here, this is a single factor of x, and then I have 2 more factors of x in my product. So that means I have a total of 3 factors of x, x to the 3rd power. Remember, what are the factors and how many do you have, right? I have 3 factors of x. And then the other thing that I have here, I have factors of y. Here are 3 factors of y. Here are 3 more factors of y. So in total, that's 6 factors of y. So this is 28 x to the third y to the sixth. Okay, so Lacey and Haley are rewriting expressions in equivalent, simpler forms. And Haley simplified the expression x to the third times x to the second, and she got x to the fifth power. Lacey simplified x to the third plus x squared, and she got exactly the same result. However, their teacher told them that only one simplification is correct. Who simplified correctly, and how do you know? Well, it goes back to what I keep talking about in class, right? 6 is 2 times 3. 2 and 3 are factors of the number 6. And because of that, because we're talking about factors here, and this exponential form shows me what the factors are, their x, and how many there are, the only one that got this correct was Haley. If you look at what Lacey was doing here, we had 2 different terms, right? Terms are those things that are separated by plus or minus. So because we have 2 different terms, we actually can't combine x cubed and x to the second. They cannot be combined via addition. They can be multiplied, and if we multiplied, we would get x to the fifth, but we cannot simplify them because they're not factors, they're terms. So next one, Haley simplifies 3 to the fifth, so she's got this 3 to the fifth power, and she multiplies that by 4 to the fifth. And she gets the result 12 raised to the 10th power. But Lacey is not so sure. She's not sure if this is correct. Is Haley correct? Be sure to justify your answer. Well, one thing I certainly can do is if these are compatible, I mean, if they're equivalent to each other, I know they'd have to produce exactly the same value. And in that case, the best thing to do is to say to yourself, where is my calculator? Oh, there's my calculator. So let's take a look at this. If I go ahead and take 3 and I raise that to the fifth power, and then I multiply that times, what do I have? 4, raise that to the fifth power. I think that's going to be a fairly large number. It is. I get 248,832. Now, I'm going to compare that with 12 raised to the 10th power. And when I look at 12 to the 10th power, what do I get? It's huge, right? This is in scientific notation. So if I look at what's on the screen there, it would be equivalent to, it's like 6.19, but I have to move that decimal 10 places to the right. So if I did that, I could write 6, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to put an extra 0 there. It's huge, right? This is much larger, 12 to the 10th, compared to 248,832. So it's ginormous. So just based on looking at them, right, they're not compatible. Now, one of the things that's going on here is like I've got 5 factors of 3 and I've got 4 factors of 5, right? I can't simplify that further, right? If I had 3 to the 5th times 3 to the 5th, that would be 3 to the 10th. But that's not what I've got. I've got different factors there. So let's move on to the next question. So scientific notation requires that one factor is a power of 10, and the other factor is a number greater than 1, but less than 10. I like how that's written. In fact, that's not, I mean, you can look at, in fact, I encourage you to look at the math notes section in this box, in this chapter, right? In this particular section, there is a math notes box that we should look at, and they ask you to see that for this problem specifically. But this is a great thing, right? Scientific notation requires one factor that is a power of 10, and the other factor is a number that's greater than 1 but less than 10. So factor, first of all, I understand factors are things that are multiplied, right? So this first number right here, this 2.56 times 10 to the 5th, is correctly in scientific notation. You can see that one of the factors is a power of 10, right? 10 to the 5th power. That's one. And the other one is a number that's larger than 1 but less than 10. that number is larger than 1, then less than 10. So because it fits this definition, this clean definition that's now my favorite way of thinking about this, right? One of them is a power of 10 and the other is a number between 1 and 10. That is in scientific notation, but the next one, 25.6, is not. Okay. Scientific notation also uses this symbol for multiplication instead of the dot or parentheses. So always kind of confusing, because when we see that, sometimes we think it could be an X. This is not an X here. It's something times something else. And it's kind of a clue that we're in scientific notation. It says none of the numbers below is correctly written in scientific notation. Explain why each one does not meet the criteria for scientific notation. Then write it using the correct notation. Okay, so for this first problem, yeah, I do have powers of 10, but the problem is that this number, right, this number is not bigger than 1, but less than 10. It is bigger than 1, but it's not less than 10. So what I can do is I can modify that by writing this as 6.25. Now I know what you're thinking, Mr. Roberts, that's not the same thing as 62.5, and you're right? So I'm going to multiply that by 10. Now, full stop, take a close look here. This thing that I underlined in green is exactly the same as 6.25 times 10. Those are identical to each other. So I'm replacing the 62.5 with 6.25 times 10. Now I have to go ahead and say, let's multiply by another times 10 to the third. The last thing I do is I have to write this as the number 6.25, but then I also have to multiply it by 1 power of 10. Well, you can see I've got a single factor of 10 here, and I've got 3 more factors of 10 here. So my correct answer would be 6.25 times 10 raised to the 4th power. So this number is in scientific notation. And that's going to be the answer that we keep. If I look at B, it's close, right? I do have the 1 factor is a number that's greater than 1 but less than 10. So I've got that. Instead of using this dot, right, we need to use this multiplication symbol, not the variable x, but this multiplication symbol. And then this has to be written as a power of x. So if I have 10 times another 10, that's 100, times another 10, that's 1,000, right? 10 times 10 is 100, times 10 is 1,000. So what we're looking at here is that this number is 10 to the 3rd power. So in scientific notation, I would write this number as 6.57 times 10 raised to the 3rd power. So this number is in scientific notation. And then finally, let's go to, there's a part C. This is not in scientific notation. To make it look like scientific notation, I would write this as 3.9, because this number right here is not a number that's greater than 1 but less than 10. It's less than 1. But I can write it as this. I can write this as 3.9, but then I have to really divide that number by 10. I have to divide that by 10 in order to make this equal to the 0.39. So full stop again. My claim is that what I've just circled, right, or that's not a circle, what I'm boxing in green, this box in green, is exactly the same as the thing that's right above it, okay? It's exactly the same. Now, when I go ahead and I write down that I'm going to multiply that by 10 to the 9th power, what I can notice is, oh, look at this. It's multiplication. I've got this factor of 10 in the denominator, right? So if I was to simplify 10 to the 9th power over 10 to the 9th power over 10, that would be equivalent to 10 to the 8th power. So this is the heart of my number, right? My number is 3.9, and then I'm multiplying that times 10 to the 8th power. And what's nice is I can verify this by throwing these into a calculator and seeing they're exactly the same. But you can see this now fits the definition of scientific notation. It is a number between 1 and 10, right? Greater than 1 but less than 10, and a power of the number 10. So if for a certain function, when you give it x, it gives you 9. Okay, so I'm reading that like that because I want you to understand what this is saying. It's saying that when you give it a particular x, and I don't know what x you give it, but when you give it that x, it produces an output of the number 9, right? If that's true, please find the following values. So here's the crazy thing, right? When I give this function f the value of x, it equals the number 9. So what I'm looking at here is 9 plus 3, right? The f of x is 9. When you give it that some particular x, you're going to get 9. So f of x, if f of x is 9, this becomes 9 plus 3, which is 12. Okay, the next one, it says 2 times f of x. Well, if f of x is 9, this is 2 times 9, so this is 18. And on the last one, it says 2 times f of x. Well, if f of x is the number 9, what do we have here? We have 2 times 9, and then plus 3 more, 18, 19, 21. 18, 19, 20, 21. This becomes the number 21. So this is an interesting problem, and it's kind of like understanding what the notation's about. Remember, f of x represents the output of the function when you give it x. So if I give this function x, and then it's going a step further and says, hey, when you give this function x, you're going to get the value 9. So I know that this is 9, this has to be 9, and this has to be 9. Then finally, question 72 is a checkpoint problem. And what that means is at this point, based on what you've done in the 7th and 8th grade, at this point, I expect that you should be able to solve these problems quite easily, right? This should not be difficult for us. And in fact, because of that, I'm actually not going to do these problems. I'm going to ask you to do them. And just as a check for you, I am going to give you the solutions, or the answers. So A would be x. Oh, I know. Okay, I'll do that. X is the number 12. And for B, x is 18. And for C, when you solve for x, you should get, no, these are the answers to the previous problem. I completely don't have these at all. Here's the correct answer. And you know what? I'm going to do this first one now because now I'm totally confused. So let me just do A just to make sure I do have the right answers here. So I've got 3x plus 7 equals negative x minus 1. If I add x to both sides, this becomes 4x plus 7 equals negative 1. If I subtract 7 from both sides, I have 4x is negative 8. And if I divide both sides by 4, we get that x is negative 2. So I think I have the correct answers here. For this one, x is negative 2. That's A. For B, you should get that x is, I think, 3/2. And if you have to, you can rewrite that as 1.5 or 1 1/2, but I like 3/2. For C, you should get that x is 0 when you solve that very carefully. And for D, when you solve it, there is actually no solution here. And that's because your variables cancel, but you also end up with a contradiction, right? You get a statement that can't be true. So there is no value of x that would make that true. So that is, those are checkpoint problems, and we will see some of these pretty soon on assessments, just because I think at this point these should be pretty easy for us, and we're looking for some mastery here. That's it for tonight. I hope you have a great evening. I'll see you tomorrow in class.